Alrighty. Good morning, everyone. How are we going? It's been over a week. And nearly 2 weeks, actually, since I've seen you all last. I hope you all had a lovely and safe Easter break. Now, the game plan for today is we are going to be pushing forward with nutrition and metabolism. I'm going to spend a bit of time recapping on what we did 2 weeks ago. And yeah, we're basically going to push right through. We're going to finish off this module and keep going strong. Again, guys, I know I basically iterate this every single week, but please, post as many things as you can in the chat on the side. You'll constantly, I can see a mirror of myself. I'm constantly glancing to the left. I'm constantly looking at that chat. Please interrupt me. Please, post your questions there. And I'll be happy to help you all out. Okay. Let's do this. Let's get started, shall we? Actually, just before I do, is the audio okay, guys? I've been tinkering with the audio again, just trying to get it better. So, hopefully the audio is all good. If not, please let me know. I've had a nasty tendency to turn into a robot a little bit lately with my voice, with cutting in and out. But look, guys, without further ado, stand back. It's time to science. Let's get into it. So what are we doing today, guys? We're going to be looking at nutrition, and we're going to be looking at, the very, very basics of metabolism. Morning, Gemma. So what we're looking at there, what we did in our last lesson was we focused a lot on digestion. So basically going from entry to exit, okay? And looking at how our bodies can try and break down sort of the food that we are eating as much as possible for the purpose of absorption. Now, we're going to go a little bit more into the chemistry behind it. Don't worry, hopefully it won't be too bad. And basically, I want to try and provide some background or some key information on the why. Why do we need to do this? Okay, so we're going to be looking at what our essential nutrients are. What do we mean by the calorie and the kilojoule? I'm sure we all know what that is anyway, but, we will touch on that. And break down metabolism into looking at catabolism and anabolism. We're going to be looking at some of the major nutrients of the body. We're going to be looking at what is a protein, what is a carbohydrate, and what is a fat. Now, that is a slippery slope. That is literally, you can do entire degrees on just one of these things. Just to put it in perspective, at Griffith University, there is a building called the Institute of Glycomics. It's literally directly next to your nursing labs. And that building is dedicated purely to the study of sugars. So it has a widely complicated role in the body. So we're just going to stick to the basics for today, especially with relation to anatomy and physiology. We're going to be looking at energy balance and look at what that means. And we're going to be looking very briefly at body temperature regulation. Oxidation of glucose, sure, but again, I will be, forgive the pun, trimming the fat on a lot of this sort of stuff because, as I said, guys, this stuff can be very complicated. It can be very, very intricate. So we will be mentioning a lot of these things, especially with the oxidation of glucose, but not going into too much detail. We will, however, be talking quite a bit about absorptive and post-absorptive state and looking at we have been going for 4 minutes and I'm already getting tongue-tied. Oh dear. Looking at glycogenolysis, gluconeogenesis, all this sort of stuff. Okay, now let's do a quick review very briefly. So this is what we kind of looked at the end of last week. Let me pop myself up here. So we take a bite out of something, okay, chew, and we swallow it down. That bolus, okay, a bolus is just like a chewed up clump of food. That then moves down our esophagus, okay, via peristalsis. and will enter into our stomach. From there, the stomach will begin to churn and mush it around, okay? And once we get that bolus that is then combined with all of these stomach acids, or stomach juices rather, that's when it turns into chyme. From there, it then will move from the stomach into the duodenum. Okay, and that's basically what we're looking at down here. Let me change to my little laser pointer. Here we go. Now, once we enter here, obviously a big problem is that in the stomach, it is very, very acidic. So we need to neutralize those stomach acids. And this is where our pancreas and the bile from our gallbladder and our liver comes into play. So with the pancreatic juices specifically, so we can see the pancreas here and we can see this sort of pancreatic duct connecting here to our duodenum. It's neutralizing that stomach acid because we don't want it to burn through our duodenum and damage this tissue. Also too is that we use a lot of different enzymes in here. So remember, enzymes are a protein and that is very, very susceptible to changes in pH. So we need to neutralize that pH to make sure all these yummy enzymes. It's gonna be a tough day, guys. All these fantastic enzymes will move through into this duodenum and do their job properly without being broken down by that acid. So some of these digestive enzymes, okay, I would expect you to recognize this word amylase. Okay, so amylase is an enzyme that breaks down carbohydrates. So what is a carbohydrate? Who can remind me? Looking in the chat quickly, who can remind me what is a carbohydrate? Any clues? Any ideas? Who can tell me what is a carbohydrate, or what is a carbohydrate made up of? Oh, come on, guys. We should definitely know this one, okay? Carbohydrates are made up of sugars. So what is happening here with this pancreatic amylase is that it is taking a carbohydrate and chopping it up into individual sugars. So I want all of you, make sure you write that down. You will definitely need to know that one. Now, looking at these other ones with trypsin, chymotrypsin, and procarboxypeptidase, would I expect you to memorize all of these names? Look, I would expect you to know at least one of these three. But what all of these have in common is that these are proteolytic enzymes. So it said a combination of both glucose and fructose. It can be different types of sugars. It's just the fact that there are multiple, like a long chain of sugars joined together. That is a carbohydrate. Well done, bud. But you are right in that glucose and fructose are both sugars. So that's fantastic. So these three are proteolytic. So proteo meaning protein and lytic, lysis meaning to split, to break apart. So these enzymes here are responsible for breaking down other proteins. And pancreatic lipase, so lipid-ase enzyme. So it helps to break down our fats. So again, I'm hoping you're seeing a little bit of a trend, a bit of a theme here, okay? Carbohydrates or sugars, protein, fat, okay? They're the big three in terms of our nutritional macromolecules. And the last one, which I did say to you guys is the lowest in terms of the priority here, but deoxyribonuclease and ribonuclease, okay, these are just for our nucleic acids, so DNA and RNA. Okay, so... Oh, excuse me. So what we were looking at before was we were essentially here. Okay, we were looking at this pancreatic duct, and obviously that's not the only thing that we have down here. We have various hormones that control this pancreatic secretion, as well as secretion from our gallbladder and from the liver. So there are two main hormones that we need to be aware of here. We do definitely need to know these ones. So we have CCK, which is cholecystokinin. And we have secretin. Now, secretin, again, helps us to get more water and get more bicarbonate. So HCO3-, that is bicarbonate. That's the chemical symbol. For bicarb. And of course, we have water. Now, that's secretin. CCK. What CCK does is essentially triggers the pancreas and triggers our gallbladder to release all of these digestive enzymes and all of that. It's basically the kickstart, okay, to get these juices into gear. Because we don't want to just be releasing these valuable hormones, enzymes and stuff like that all the time, because there's no need. It's a waste. So that's what we did a lot of the week before rather, in week 6. So what I want to do now is move forward into looking at more of these raw materials that we are trying to get, okay? We are trying to break down and absorb these sugars. We are trying to break down and absorb these amino acids, because remember, amino acids make up proteins. We're trying to break down these fats because that was the entire purpose of us eating, to get these nutrients, get these vitamins and minerals and all these good stuff so that we can replenish our body and regenerate and build and grow. So, nutrition, okay? It is the source of fuel that provides the energy for all biological processes, okay? We are not solar powered, okay? We cannot just rely on the sun's energy or anything like that. We need to eat as a source of energy. We also need to eat as a source of materials. You can't, turn around and say, I want to build a house. I want to build a brand new home for me to live in. And they go, okay, you want to build a house? That's great. What have you got? And you go, I've got an idea. Okay, you need materials, you need building blocks, you need concrete, you need timber, you need nails, and I'm sure many other things to build a house. But you need these raw materials to build things, and we as a large multicellular organism are no exception to that rule. We need building blocks, okay, and we need also maintenance. We have cells that are dying, we have cells that are being damaged, being worn out, and we need to replenish and rebuild them. So eating, in other words, is very important. Now, this nutrients, we've got our major nutrients, okay? These are our macronutrients. This is what I've basically been describing thus far. So we've got, our carbohydrates, our lipids, our proteins. These are the big boys, as it were. This is what the majority of what we are eating is subclassified into one of these major three. We've also got these micronutrients, so vitamins, minerals, these sorts of things. Now, we also have our essential nutrients. So what that means is our body is incredibly clever, okay? So when, just for instance, with our proteins, we have 20 common amino acids. So these 20 amino acids, if you put them in, if you join them up in a very specific sequence, that is how we make our proteins. Now, what is actually really, really, really cool is of those 20, only 8 of them are essential. Now, what do we mean by essential? What that means is that our body cannot do any trickery to make that amino acid. So what that means is, for the other sort of 12 or so non-essential amino acids, is that our body can take one amino acid and convert it into another amino acid. Which is really cool. It's really useful. However, that essential nutrients, what that is essentially describing for us is that we are unable to convert it or synthesize it or make it ourselves by using whatever resources we have in our body. Okay, we need to get it from an alternate source. Sorry guys, just bear with me. I just need to change the blinds. Sorry, that's a bit better. There we go. Sorry about that, guys. Okay, so that's what we're talking about here with nutrients and what we're trying to do in terms of eating. Now, food energy. So in science, in chemistry and stuff like that, we use joules. Let me do this. In Australia as well, we do use joules or kilojoules. In America, they use like calories and stuff like that. So what essentially it is describing here, especially with the calorie, this is the amount of heat or the amount of energy, because remember, heat and energy are one and the same. Heat is just a form of energy. It is the amount of heat that is required or energy rather, to raise the temperature of 1 gram of water by 1 degree Celsius. Look, is that important for you guys to know and memorize and have firm in your mind with nutrition and A&P too? Not really, no. What is important here is that food, it contains energy. Okay, and we can quantify, we can measure that amount of energy that food has, which is why, especially now with a lot of nutrition, like a lot of dietary labels and stuff like that, it tells us the, how much energy that food contains. Like, if you turn around to and eat like a massive, large pizza with extra pepperoni and extra cheese and just extra good stuff, okay, that's going to have way more energy or way more calories or kilojoules than, say, a bowl of lettuce. So, because what we're doing is we can break down all of the, components of our delicious pizza and turn that into energy and fat. Now, during the breakdown, carbohydrates and proteins yield about 4 kilocalories per gram. So, proteins and carbs have a decent amount of energy. Fat has a lot of energy. Alcohol also has a lot, but we're not going to talk too much about that. And of course, it all comes down to energy in versus energy out, okay? If you want to lose weight, if you want to, burn fat, then the energy out, the energy that you're expending, must be greater than the energy that you are putting in. And it is as simple as that. That does not mean it's easy, but it is simple. This is also why many athletes, for instance, like there are some power lifters, like the world's strongest man and stuff like that. They can have, the recommendation is, sort of 2,000 calories a day, or 2,000, 2,500, around that mark. Some of these guys can have over 10,000 or 12,000 calories. But again, they are pushing their bodies so hard that it is still, they can still be at risk of losing weight because they are expending more energy. There was also a study done, I don't know the validity of this study, so take it with a grain of salt, where he essentially, I think it was a professor in America, ate nothing but Twinkies, so like little packaged cream cakes. He ate nothing but that for a month and a half. That was it, for all of his meals, anytime he ate. But he limited the amount he was eating based on this energy in versus energy out, and he did lose weight. It's not to say it was healthy, but he did lose weight. Okay, so let's talk now about some carbohydrates. So it is a complex array of sugars. As I said, like if we take a sugar molecule and another sugar molecule and we join them together, and then another one and another one and another one, and like sort of layer them across, that is what a carbohydrate is. Now, where do we find carbs? We find them in a lot of grains and vegetables and stuff like that. Now, we also have our saccharides. So saccharide means sugar. So if I say monosaccharide, mono means one. So monosaccharide means one sugar. So like glucose or fructose or mannose, stuff like that. If you have a disaccharide, di means two, saccharide means sugar. So that's two sugar molecules that are joined together. So the main sort of prefixes you would need to know for that is mono means one, di means two, oligo, so O-L-I-G-O, oligo means sort of a couple. It means anywhere from sort of 3 to 10-ish. And once we're past 10, it's basically, we just call it a carbohydrate. So that is what we're looking at here with carbohydrate. Now, the big thing is with carbohydrates is, as I've mentioned, it is literally just a chain of sugars that are joined together. And what that means is that it is, obviously depending on the complexity of the carbohydrate, a good and relatively easy source of energy. It's quite quick. We don't have to do a whole lot to it. Again, depending on the carbohydrate, of course. And that's what essentially is being described here, is that, we've got our carbohydrates, they break down quickly and can release these glucose molecules rapidly into the bloodstream. Now, when we're looking at this GI, okay, this glycemic index, what this is essentially how similar or how quickly that sugar can be compared to just pure glucose. So, glucose would have the fastest in terms of this glycemic index because it's already in its glucose form. It's just straight sugar. So it's straight through. You don't have to break it down. There's nothing too complicated going on there. Whereas the more intricate, more complicated this carbohydrate is, the longer it takes the body to break it down into those individual glucose molecules and release it into the blood. And that's what we're seeing here. So our low GI foods, a lot of these fruits and veggies, whole grains, what the medical experts are telling us that we should be eating a lot of. Our medium GI here, so it's a little bit more simple for us to break down. And our high GI means it's even simpler again. So like white bread, for instance, if you what I was saying in our last class is that we've got that salivary amylase. If you actually take a big bite of bread and you just chew it for like a couple of minutes, like at least 2 or 3 minutes, you will notice that bread will start to taste really, really sweet because that salivary amylase is starting to break down the carbohydrates that are found in that white bread and turn them into sugar. Turn them into glucose, which is activating your sort of sweet taste receptors in your mouth. So that's carbohydrates. Now we have lipids. So lipids are our fats, and it sort of should be quite low in terms of our dietary intake, around sort of 10% or less. Now, Sydney's in the lecture, but her chat box is not working. Okay, cool, no worries. Thanks for letting me know. Let me do this. Here we go. So when we're looking at our fats, basically a lot of these fats can be from nuts, it can be from oils, it can be from various meat products. So like, if you get like a steak or something, it can be marbled with fat. So that's one type of intake there. Also, eggs is also a very good source. So inside the yolk there's a lot of fats and cholesterol and stuff like that. I'm going to talk about these all a little bit more in depth when we look at how we can chemically break them down in terms of and absorb them. And the last thing I want to talk about here is looking at our protein nutrition. Okay, protein, one of the best and I guess you would say simplest sources of protein are animal products. So looking at meat, looking at eggs, looking at milk or dairy products, and that's like even what a lot of protein supplements are. So like your protein powder, your whey powder. Okay, that's sort of coming from milk and dairy based products. And the big thing is that it is just a good holistic source of amino acids that have a lot of the key essential amino acids that we do need in our diet. Now, that's not to say that you are forced into that. Obviously, you can have a vegetarian or vegan based diet. However, it's just a little bit more complicated, a little bit more difficult to do so, just because you will require either more in terms of the quantity, or just a different combination to make sure that you are getting the appropriate level of amino acids. Now, the recommended daily intake, look, I don't like to go too much on these because it just depends so much on your body's need. So for instance, you might have this sort of recommended daily intake. However, if you are an elite athlete, you're going to need way more of this. And that's what it's sort of saying down here. If you're under physical stress, if you are injured, you will need more of, more protein intake to help you heal. If you are pregnant, you're basically going to have to increase on all these, on carbohydrates, lipid, and protein. So ultimately, your diet should be adjusted and should accommodate what you are doing physically, to ensure that what you are, fueling your body with is enough to, meet those demands. Okay. So, metabolism. What we're doing here is that essentially we have ingested, we have digested, and we're now absorbing these key nutrients. So look, our sugars, our amino acids, and our fats. Now, within the world of metabolism, we have two main terms here. We've got catabolism. So catabolism is taking one big thing and breaking it down into smaller, more simple things. Okay, so that's catabolism. And anabolism is the opposite. That's where I take many smaller things and build them up into one big thing. Now, I think... okay, it must be later on. That's fine. We'll talk about that in a moment. Excuse me. So how I want you to think of this is like, let's say we have a burger. Now, let's say I take my burger and I take the top bun off, and I take the lettuce off, and I take the onion off and the meat patty off, and I sort of take my burger and I just deconstruct it. That is catabolism. Okay, I'm taking my one more complicated thing, my burger, and I'm breaking it down into simpler components. Now, anabolism would be me taking the lettuce, the patty, the bun, sauce, all that sort of stuff, and then building it into one burger, okay? That sort of synthesis, that is anabolism. Okay, so let us now start to really dig down on these key sort of macronutrients and tie it into what we were doing last lesson here. So again, digestion of proteins. So I've eaten, say, a ribeye Angus steak, which I did a few days ago, and it was delicious. What is happening there? Okay, I don't have a steak receptor in my body. Okay, I have no way to just go steak and just absorb it straight through into my bloodstream. I need to digest it. I need to break it down. Okay, I need to catabolize it. So where this starts is, and this is very much, guys, chemical digestion that we are looking at here. So obviously mechanical digestion is happening in the mouth. We're breaking it down. I'm tearing it up with my teeth, and then it goes into the stomach. Now what we see here is that the acidity of my stomach is causing my proteins to denature. So what do we mean by denature? It means that the protein, being this like very intricate and complicated folded structure, will sort of unfold and unwind and not work properly. So what we see there too is that our chief cells will then release this pepsinogen, okay, then be converted to pepsin because of the acidity of our stomach, and we'll then begin to sort of chop up and break down our the proteins that were involved in that steak that I was eating. Now, obviously, once it's sort of been churning and mixing around in my stomach, that chyme will then move through out of the stomach and into my duodenum. So that's where we see the release of those hormones we're talking about, secretin and CCK. And what that is going to do is it's going to neutralize the stomach acid from that chyme in my duodenum, And it's going to release a bile. It's also going to release these pancreatic juices. Now, remembering with the in the pancreas, we've got those key proteolytic enzymes like trypsin, chymotrypsin, and procarboxypeptidase. So these enzymes, these proteolytic enzymes, function, and what they do is they, again, think of them as like big chemical scissors. They're going through and they are chopping up our protein to give off these individual amino acids or small groups of amino acids. And that way, these small sort of chunks of amino acids, we can then absorb them in the small intestines, and they then go through to the liver and can then be synthesized. Does that make sense so far, guys? I'm not seeing many questions in the chat so far. I hope that means that everyone's all good. But again, please feel free to interrupt me or let me know if you do have any questions. Now, looking at, let me do this. Here we go. So now looking at digestion of carbohydrates. So you'll notice that, again, this is a bit different compared to our digestion of proteins. Proteins really only started its chemical digestion in the stomach. There was nothing there that was sort of starting in the mouth per se. However, when we look at our carbohydrates, it definitely does start at the mouth. So what we see in the mouth is that salivary amylase is already starting to break down those carbohydrates and starting to chop them up into those basic sugars. Again, like what I said before, if you take a piece of white bread, take a big bite out of it and just chew it for a few minutes, you will find it will start to taste sweet. Now, you then chew, and then swallow, and then it will move into the stomach where our salivary amylase is destroyed. Why? Because salivary amylase is an enzyme, and enzymes are a protein. So what that means is that when we chew and swallow, that salivary amylase will fall into our stomach and will undergo the same process here. Okay, it will be denatured, it will be broken, and it will be dismantled and essentially recycled. Now, from the stomach, it will then move through into the duodenum. Again, we see the release of CCK and secretin there. And then what we're going to see is that pancreatic amylase. Now, that pancreatic amylase kind of picks up from where salivary amylase left off. So you'll notice, again, they're both called amylase. The only difference here is that salivary amylase or pancreatic amylase. And again, this is just reference to location. What that is then going to do is to continue chopping up those carbohydrates, and then these brush border enzymes will further facilitate that breakdown. So in the microvilli there, those little microvilli hairs that are on the small intestine. So as the carbohydrate comes in contact, it'll further sort of chop them and sort of snip them up. And then those much smaller sugars can then be absorbed through the small intestines there and transported to the liver. Now, what's happening down here with the liver? We're going to talk about that a lot more in a moment when we talk about absorptive and post-absorptive states. But essentially, our liver will control what we do with glucose depending on how much glucose we have in our system. But again, we'll talk about that in a moment. Okay, now, digestion of the lipids. Technically, as I've said before, it does start in the mouth. There is a salivary amylase, but it doesn't have a massive role with that chemical breakdown. So I'm happy for you guys to just say, look, nothing happens in the mouth, nothing happens in the stomach, and it's only really once it gets down into the small intestines there. And the big thing that's happening at the beginning here is that bile that's being released causes it to emulsify. Now, do I have an image? No, that's okay. So emulsification is where we take one big blob and we break it down into lots and lots and lots of little blobs. And this is just so it's easier for our pancreatic lipase, that enzyme in there, to get in and break down these little drops, to break down these triglycerides. So just to put it in perspective here, this is a triglyceride. It's also called a triacylglycerol. It's just another name for it. So how does it get the name triglyceride? So tri meaning 3, 1, 2, 3. And this is a glycerol backbone. So what this pancreatic lipase will do is it will essentially, like where my little laser pointer is, it'll cut 2 of these. It will snip them off, and then this sort of glycerol backbone here and this one fatty acid will then be moved into these chylomicrons. This is a little sort of protein sort of vesicle, like a little bubble, and will then be transported via the lymphatic system. So again, we need to be aware of that with our sugars, like carbohydrates, our proteins, and our nucleic acids, they all move via the hepatic portal. So it goes into just our bloodstream, will go straight to the liver to be processed. The fat, however, it does not move by that route. It goes via the lymphatic system. Now, you can see the way I've bolded this is that can be like a useful little way to help you remember this, okay? Lymphatic system. Now, chemical digestion of nucleic acids. Look, do I expect you to know this? Sure. But proteins, carbs, fats are far more important. Far more important. You should definitely be prioritizing those 3 before you get into nucleic acids. So basically, this is what a nucleotide looks like. And what it does is it will break that down into its nitrogenous bases, pentose sugar, and phosphates. What that means is that our nucleotide, so this is what our DNA is made up of, it's going to cut here. So that's going to release this nitrogenous base. It's going to cut here to release this sugar. And it's going to cut here so we have our phosphate. It's just going to basically take those 3 major components and just break them apart and send them on their way. Nice and simple. So that happens in the duodenum and in the small intestines. Oh, I thought I deleted all this. I was supposed to do that. That's okay. Now, this is essentially, this must be where I got the burger idea from. What I was talking about here, this catabolism and anabolism, that is what is being described here, okay? So when we were looking at our carbohydrates, our lipids, and our proteins, what we were looking at there is essentially catabolism. We were taking one big complicated thing, like a big complicated carbohydrate or a big complicated protein or our triglyceride, which isn't overly big and complicated, but it can be, and breaking them down into their smaller, more simple components. And that does yield us energy. Now, anabolism is, again, taking those smaller or component pieces and building them up into something different. So, for instance, if you take a heap of Lego blocks from one big construction, like if you've made like the Hogwarts or something like that, Hogwarts castle out of Lego, and you take all those Lego pieces and you break down the castle, but then you make a rocket ship. Okay, that building the rocket ship based on those individual pieces, that's our anabolism. Now, I don't know if I'll be able to show you this properly. That's okay. I'm going to link this to you guys in the chat here. Let me just come back over here. Here we go. But this, I just want to give you a little bit of an indication into how complex metabolism can be. And this is one of, I think, 4 different pages. Okay, it is immensely and wildly complicated and something that I had to endure in my second year of biomedical science. And we can see like we've got the citric acid cycle here, we've got glycolysis, we've got breakdown and synthesis of various amino acids, blah, blah, blah. Do I expect you guys to know all of this? Absolutely not. Absolutely not. And why am I showing you this? 1, to show you that human metabolism can be pretty scary, okay? There's a lot of stuff going on here. And 2, I guess reinforce or tell you guys, like, I will be simplifying things quite a lot with this next metabolism module. So again, this is just vastly oversimplified. So we take these simple molecules, we break them, or these more complicated molecules rather, we break them down, we release energy from it, and then we can take these simpler forms and rebuild them into the things that we need. Now, not only is that important for us in terms of obviously, anabolism and building, the key blocks that we need to survive. Perfect example is like we were talking about salivary amylase. And when salivary amylase moves into the stomach, it gets destroyed. So we kind of need to replenish that. We need to make more salivary amylase. Otherwise, obviously we're just going to run out. Another very important part is that it's very important for us in terms of regulation of our body temperature. Okay, this metabolism, when we have this generation of energy, it's generating heat. Okay, and we use that to control our body temperature. Now, I'm not going to go too much into the whole homeostatic control of how we control our body heat. We might do that a little bit in the Tute workshop, but yeah, I'm not going to talk too much about the body temperature regulation. It's just we are obviously warm-blooded, and by eating these foods and this chemical breakdown, we are obviously releasing energy and releasing heat. Okay, so what are we looking at here? Again, this looks very, very complicated, but what is happening is we have just eaten a big, wonderful, glorious meal, and it's moved through the mouth, moved through the stomach, it's then small intestines, and it's been absorbed. And what I've essentially said to you guys is that those key nutrients will then be absorbed and moved to the liver. Okay. Basically, that's where we are now. So we've got these liver lobules. Okay, that's the sort of this functional sort of hexagon unit of the liver, and this is where that nutrient that we've just absorbed goes. And this is a really good summary slide on what happens to each of these key macronutrients once we've absorbed them. So for instance here, when we're looking at our carbohydrate metabolism, it ultimately comes down to like how much sugar we already have in our bloodstream. And, we can either store it as a carbohydrate or store it as fat, or we can release that glucose through the blood and to feed and fuel our tissues. What we see over here is some lipid metabolism. So we can take those lipids or turn it into cholesterol. We take that cholesterol, turn them into, a triglyceride if we want to store it as a fat, or, we can take those triglycerides and break them apart. Again, I want you to picture in your mind that this is like a seesaw or like a set of scales. It is a constant balancing act that your body is trying to do to keep you healthy and alive. Okay, how much do you have enough sugar? Do you have too much sugar? Do you have enough fat? Do you have too much fat? It's this constant up and down balancing game that our body is trying to do in order to keep you alive and healthy. And of course, up here, we also have our protein metabolism, okay? And this is where we can see that conversion of one amino acid to another amino acid. We can convert it into various proteins, or what we can see here is gluconeogenesis. So gluconeogenesis, big complicated word. What does that mean? So gluco, meaning glucose, neo, meaning new, genesis, meaning to generate, to create. So if we translate it, it basically means glucose, new, make. And essentially what it means is that we take something that isn't a sugar and we can convert it into a sugar, which is pretty cool. So we can take, like, if we have excess amino acids, we can convert them into sugar. And the byproduct of that is that we release urea, which obviously will then go to the kidneys and be released in urine. Okay, now again, this wonderful page here, okay, this digestion, this like stage 1, stage 2, stage 3, what you are looking at here, if we not even look or include this top part, okay, if we just completely ignore or disregard that, just this part and this part is like looking at sort of all of this, all of down here, all of this part, and sort of all across here. So all I want you guys to know is that we take these proteins, we take those carbohydrates, and we take these fats. And there are 3 key processes. All I want you to do is just know the name of them, okay? We have glycolysis. So glyco, okay, glucose, sugar. Lysis, to split. It's the process in which we break down sugar into pyruvate. We then move that pyruvate, we move these fatty acids, or we move these amino acids into the Krebs cycle. Krebs cycle, also known as the citric acid cycle. Okay, and what that does is we can then, the last stage is this oxidative phosphorylation. And that is basically where we convert all of that into ATP, adenosine triphosphate. And that is our energy. That's what we use to fuel and power our body. Now, again, this is very, very complicated. What do I expect you to know with all of this? Protein, carbs, and fat, we break them down. It goes through these processes to create ATP. That is the big final product. That is the aim of the game. That's what we're trying to do here, is have ATP, have energy. Does that make sense, everyone? That's a lot of info that we just kind of smashed through quite quickly there. Is everyone okay? Look, guys, what we'll do is, whoopsies, here we go. Guys, let's have a quick 5-minute breather, okay? Stand up, stretch your legs, go for a quick walk around, and we will then push on to look at these absorptive and post-absorptive states. So we will resume at probably sort of 9:26, 9:27-ish. Ooh, there we go. All right, guys, let us resume. When my chair isn't getting stuck. So yeah, got some nice chilled out tunes going on there. Thought I'd go for something a little bit acoustic, something a little bit more laid back, seeing as you've got your exam coming up soon. So we'll try and keep you guys nice and chilled out. So where were we? We were looking at metabolism. Again, this is enormously complicated, but the big things that we need to be aware of here are these three main processes, so glycolysis, Krebs cycle, oxidative phosphorylation, and that essentially all three of these things, okay, like, we've got our glycolysis, so it might sort of feed in to glycolysis here, like our fats and our proteins and stuff like that. But what they all have in common is that a lot of them, we've got some infrequent ones here, but the majority of them will pass through this acetyl-CoA. That then feeds into our Krebs cycle and our oxidative phosphorylation. Now, let us look at absorptive and post-absorptive state. This is very, very important. So, what time is it? 9:30. So, I think pretty much everyone here should be in an absorptive state, okay? This is essentially triggered after we have eaten something. And what is essentially happening here is that by, eating stuff, we are getting more amino acids in our blood, we're getting more glucose in our blood, we're getting more glycerol, more these fatty acids, okay, so they get these triglycerides in our blood. And what that means is that we can essentially use that for fuel. So looking at this absorptive state, okay, it's around 4 hours after eating a meal. Again, it varies a whole lot depending on the meal that you've eaten and the size of it. Don't freak out if this looks blurry as hell. This is blurry as hell for me as well. I need to try and change this image. Now, what we're seeing here in our bloodstream here is that we're seeing a lot of glucose, we're seeing these fats, we're seeing these amino acids. And what is going to happen as a result of this absorptive state, we're going to see a lot of different processes occur. One of them being like glycogenesis, so the creation of glycogen. So glycogen is the storage form of glucose, okay? We store it in two main places, in our liver and in our skeletal muscle. And this is like our short-term energy response. We can see things like, to increase the synthesis of glycogen within our muscles. We can see lipogenesis, okay, to create more fat, okay, to store it away for a rainy day. So let's talk a little bit more about this absorptive state and what is actually happening here, because what we're looking at here, I would expect you guys to have this memorized at the minimum, okay, at the bare minimum. So the main stimulus here, the main thing that's kicking all of this off is this increase in blood glucose. So again, why do we have this increase in blood glucose? Well, because we've just eaten. We've just eaten a big meal. Let's just say I ate, I don't know, Cocoa Pops. Let's just say I had a massive, massive bowl of sugary Cocoa Pops, okay? I'm going to chow those down. That's then going to be broken down. I'm going to absorb those sugars. And what's going to happen is my blood glucose levels are going to increase. Now, what is then going to happen is that will stimulate the beta cells, okay? The beta cells of our pancreas, and that will cause it to release insulin. Now, insulin is a very, very interesting and fascinating molecule. And what it will essentially do is it opens the gates, okay? It's sort of like the key that unlocks a heap of doors in our cells. And it does a whole lot of different things, like allowing this facilitated diffusion of glucose into the target tissue cells. What that essentially means is that we can have glucose moving around our blood, and insulin will allow the door to open so that glucose can move into your cells. And what it's also going to do is it's going to trigger the active transport. So it's going to forcibly move a lot of these amino acids into your tissue cells. Why? Well, if you've got the amino acids, so you've got the resources and you've got the money to do it, like energy, like sugar, then your body's going to say, righto, let's start making some stuff. And what we're going to see here is an increase in protein synthesis. Okay, if we've got the Lego pieces to make it and we've got the energy and money to do so, let's start building. Now, as we look here, as the glucose moves into these target cells, we're going to see cellular respiration or aerobic respiration. That's the predominant one. And that's where we use oxygen and glucose to produce ATP. In other words, this process, okay? So we're going to take that, let's say this. We've got a slice of toast with ham and cheese. Okay, that's what we had for breakfast. Nice balanced diet. That's obviously going to be moved through the stomach. It's going, or our GIT. It's going to be broken down, digested. All those sugars and fats and proteins are going to be absorbed. This is going to very clearly trigger us into an absorptive state. And it's going to then allow us to create more energy. We're going to create more fat, okay? Because we want to save that energy for a rainy day. We don't know when our next meal is, okay? When, millions and millions of years ago, we did not have a Woolworths down the road or an IGA or a Coles or whatever shopping center that you go to, okay? We didn't have that. Your body didn't know when its next meal was. So instead of eating something, wasting all the nutrients and minerals and stuff, and then just dying because of starvation, we save it for a rainy day. And again, that's what we're seeing here, okay? We're seeing these, key nutrients floating around in the blood, and these are the main responses that we are seeing. Okay, now, post-absorptive. So what that means is, let's say, we've had our, let me do this. So let's say we've had our breakfast, we've had our, ham and cheese on toast, and it was delicious, and it was very yummy, and we're happy, and we're content, and we don't eat for another 6 or 8 hours. What's going to happen then? Well, your body is going to start essentially preparing or try to restore these levels because we don't have any of these nutrients because we haven't eaten. So again, looking at this graph here, if we have a decrease, a lowering of these plasma glucose, what that's going to do is that's going to trigger the alpha cells. Okay, please don't get that muddled up. That's a common thing. A lot of people get beta and alpha muddled up. Beta cells are insulin. Alpha cells are glucagon. Now, another common area of confusion is glucagon and glycogen. Glycogen is a carbohydrate, okay? It's multiple glucose molecules are joined together. Glucagon is a hormone. So glucagon will trigger glycogenolysis. So glucagon will trigger glycogen to be broken down. Now, why would it do that? What is the purpose of that? Again, we are in a post-absorptive state. Your body needs fuel, but we haven't eaten anything. So we can't just shut down and our cells just die. So what's going to happen is this glucagon is going to do several things. It's going to trigger your liver to break down those glycogen stores. Where did those glycogen stores come from? From here. So when you were eating your breakfast, when you had plenty of excess energy, you stored it as glycogen. Okay, you put some money, you put some away for a rainy day. When this process is kicking off, that's the rainy day. So it will take that stored glycogen and break it down into those individual glucose molecules and circulate them around the body so the body has fuel. Now, at the same time, it will also trigger the breakdown of adipose tissue. So adipose tissue is where we store fat. So it's going to break down fat into, and then sort of send it to the liver for conversion into, sugar and energy, or feed it through into that citric acid cycle so we can use it for fuel. Now, this process is incredibly complicated and it takes time. It takes a long time, whereas the breakdown of glycogen is much faster. So even though both of these things will trigger at the same time, this one will happen first. Now, what is then going to happen is that we see a negative feedback loop. What this means is that this process will continue. It will keep going until we see a sudden spike in our glucose levels. So what might cause that spike? If you suddenly go, oh my God, it's been like 6 or 7 hours and I haven't eaten yet, and you finally have something to eat, okay? Your body, by eating that, you'll then absorb all of that nutrients. You'll get a big spike in your blood glucose levels, and it will turn this process off. Which again, makes sense because we don't want to be, freaking out and using all of our stored up nutrients that we've saved for a rainy day when we've just gotten a huge flood of nutrients. Does that make sense, everyone? Is everyone okay with that? Because I would 100% expect you all to be able to explain clearly to me what is an absorptive state, what is the post-absorptive state, and what are the main differences between them, as well as looking at what is the sequence of events that can occur with a sharp increase in blood glucose, and the same thing with a decrease in blood glucose. Okay, I would expect you all to be able to understand and explain that to me. Okay, so what are we even saying here? Carbohydrate metabolism. Okay, so in our GI tract, again, I've explained this to death and back, basically, is that we take these long chain carbohydrates, we break them down into their simple sugars. Cool. Now, in the liver, we then transform some of these simple monosaccharides like fructose and galactose and mannose and all that sort of stuff, and we convert them into glucose. Glucose is sort of the main molecule that we use, okay? Because take that one glucose molecule and we join them up into a long chain, and that is what we have, glycogen. Now, in our inside of our body, okay, we can break down that glucose to form energy, okay? We can convert it into amino acids. So we can take an amino acid and turn it into a sugar. We can take that sugar and turn it back into an amino acid. We can do all sorts of different things. And we can turn it into a fat, okay, for that long-term storage. Now, what we're seeing here is, again, just a bit of a simplification. Look, what we are essentially describing here is gluconeogenesis and glycogenesis. So gluconeogenesis is the creation of glucose from a non-sugar source. Okay, so glucose, sugar, new, genesis, to create. Glycogenesis, so glycogen, and genesis, to create. And what this is essentially showing is that, look, we can take this triglyceride and we can break it down into glucose, and we can turn glucose into glycogen and stuff like that. We can take amino acids that we're not using at that time, and we can break it down into glucose. So in the event of starvation, if we are running out of fuel, we don't have enough sugar, we don't have enough nutrients, what we can essentially do is take excess or take some amino acids, and we can take some of these fats and break them down into glucose, which we then use for fuel. Okay, so looking at our lipid metabolism, we are very, very good at synthesizing and creating the fats that we need. There are only 2 essential fats that we actually need in our diet, okay? And that's linoleic and alpha-linolenic acid. basically, if you the nomenclature and how we count it, I'm not going to bore you too much with this, is depending on the double bonds at the very end of this tail. But if we're counting from this end, we refer to it as an omega. So omega-3 and omega-6 fatty acids, like your fish oils and your stuff like that. That's why we need to have those in our diet, because those are the only two real essential lipids that we need. Again, I'm super not going to go into into complex detail on lipid metabolism. All I expect you to know is that if we have excess sugar, okay, and we have excess fat, we can take these fatty acids and make a triglyceride. If we are in a period of starvation, if we are needing more energy, we can take a triglyceride and we can break it down and recycle it and essentially create it into sugar and create ATP and use that as energy. Honestly, that's pretty much all I expect you to know with that. Again, I'm super not going to go into the super nitty gritty here, because it's a bit of a runaway train. All this slide is doing here is reinforcing what we were saying over here. Okay, we can take a fat, we can break it down, that glycerol, into glucose. You can take the fatty acids and create into energy. What do I expect you to know here? All I want you to really be aware of here is that when we're looking at the breakdown of lipids, we can create what are called ketone bodies. Okay, so these ketone bodies can cross the blood-brain barrier, whereas our fatty acids cannot, because they're far too big. But the problem is with ketone bodies, if you have too much of it in the blood, it can lead to a state called ketoacidosis. And this is unfortunately a side effect too of diabetics, okay, and it can smell like alcohol. So there have been some cases where some diabetics have been on the side of the street. They haven't had any any sugar or insulin to sort of help them out, and people have walked past and they've just thought they were drunk, because they can just smell all the alcohol in their breath, when no, it's actually not. It's this ketosis that's occurring there, and they get mistaken for just being intoxicated when they're not. Now, protein metabolism. Again, we were talking about this before. What we are looking at here is an amino acid, which is drawn incorrectly. That should be an NH3, and that should be O-. But anyway, these amino acids have three things in common. Every single amino acid that we have in the body, okay, will always have this quaternary ammonium group. It will have this carboxylic acid. It will have this hydrogen, and it will have this carbon. So those things are the same for every single amino acid. The only thing that changes is this one group up here. So if we swap these out, then that's how we get our different amino acids. Now, in the process of protein metabolism, obviously, if we are to convert one amino acid to another, all we need to do is change what this R group is. So, for instance, if I take glycine here, I remove this hydrogen, but I put this CH2, this methyl group, and this sulfur, SH, on there instead, suddenly I've got cysteine. Okay? This here is tyrosine. If I was to delete this OH group, you would have phenylalanine. Again, I don't expect you to know all of the amino acids. That's for my poor biochem students to suffer with, not you guys. It's okay. But the big thing is that this is what I was saying by the essential and non-essential amino acids. So converting tyrosine to phenylalanine is non-essential. We can convert it from one to the other in the liver, and that is indeed what we do. Now, if we do have an excess amount of protein, what we can do is we can deaminate it. Now, what is deamination? Well, this here is called an amine group. Oops. Uh-oh. There we go. again, I'm trying not to get too much into the chemistry of it, but this is called an amine. So deamination is removing this amine from an amino acid. And what essentially happens there is that those amines get converted to urea, which is just multiple NH2 groups connected, and that is then released in the urine. Okay, it's filtered out by the kidneys and it's released as urine. And what we can then do is take that amino acid that has been deaminated and, convert it into glucose. So we can turn those excess proteins, we can turn these excess amino acids and essentially convert them into glucose by gluconeogenesis. Okay? So again, it's just the big takeaway message from this is obviously understanding these keywords I'm saying, like gluconeogenesis and everything like that. But it's also, I want you to just, I guess, appreciate how versatile and how resourceful our body really is, in that we are able to take whatever we've got on hand and synthesize it into these key materials and key nutrients that our body requires. So when we're looking at our protein metabolism, the big thing here is that we will either oxidize and convert it, and convert it into energy, or we'll convert it into fat for storage. We actually cannot store proteins. We cannot just store away amino acids. It's not that simple, I'm afraid. Now, this is just going into a lot more detail into what I was explaining before, what was being explained on this slide here. But in essence, what is happening here is that the liver will remove these NH2, this amino group, and convert it to urea and remove it. And we can either have it enter the Krebs cycle, which is also known as the citric acid cycle, to produce ATP, or we can then convert it into glucose via gluconeogenesis. So that's some of the pathways that we can use for protein. If we do have excess amino acids and we need more sugars, that's what we can do with it. Okay, vitamins. Okay. Vitamins, guys, basically what I want you to do when we're talking about our fat-soluble vitamins, I want you to think of a dad bod. Everyone knows what a dad bod is, yeah? Like you got the dad bod, he's got the big, the big fatty tummy. And what does a dad do? Every dad wants to build a deck, okay? He wants to go out and build a big wooden decking out the back. So guys, when you're thinking of fat-soluble vitamins, just remember that dad bod, and that all dads want to build a deck. A-D-E-K. So vitamin A, vitamin D, vitamin E, and vitamin K are all fat-soluble. So that's a good little trick, a good little mental trick there to help you remember those fat-soluble vitamins. Dad bod is fat. Dads want to build a deck. A-D-E-K. Now, our water-soluble vitamins, which we obviously have a lot more of. Look, I'm not going to go too in depth. I'm not going to go too ham here with our water and fat-soluble vitamins. The big ones here I just want you to be aware of is vitamin C is a big one. Okay, vitamin C is very important for it works as a coenzyme to help proline to get converted into, I think it's oxyproline, and what that does is essentially helps hold a lot of our connective tissue together. And if we don't have that, that's where we get scurvy. So it affects like wound healing and holding those key connective tissues together. The last one down here is mainly vitamin B12, okay? This is where our intrinsic factor came in. We had to release that intrinsic factor from those parietal cells in our stomach to help us absorb this vitamin B12. And that really helps with a lot of things like DNA synthesis and maturation of our red blood cells and stuff like that. Very, very, very important. All right, guys. So again, we covered a lot of stuff here, and nutrition and especially metabolism is an incredibly complicated and intricate field. Big things here I want you to be able to do is understand and really be able to explain to me how it is our body is able to digest and break down carbohydrates, fats, and proteins. Incredibly important. Understanding what is happening with glycolysis, gluconeogenesis, glycogenolysis, okay, glycogenesis rather, okay. What do those words mean? You need to be able to define them for me. Understand what is happening with absorptive and post-absorptive states. What hormones are being released, okay? Insulin and glucagon. And what are those two hormones doing to ensure our body essentially survives? Okay. Guys, are there any questions? Any questions, queries, anything at all? Look, I'm going to be hanging around in the chat for a few minutes anyway. Look, thank you all very much for joining me today. This one was a nice, short and sweet lecture, which is good. Give you a little bit more time to do some revision for your mid-trimester exam, which we'll talk about a little bit in the Tute workshop tomorrow. Guys, have a lovely day. Study hard, do your best, and I will see you all tomorrow.